Hello, today we will be solving a frame. We will be drawing the internal force diagrams of a frame. So we have a column, a beam, and another column here. And I have a roller support here. A uniformly distributed load that's equal to 5 kilonewton. The magnitude is 5 kilonewton per meter. And we have a point load whose magnitude is equal to 10 kilonewtons. The height of the column is 4 meters. This height is 2 meters and the length of the beam is 5 meters. And let's put some labels here also: A, B, C, and D. And what we want to do is to calculate or determine the internal force diagrams, draw the internal force diagrams of this frame. But before doing that, as an exercise, let's do the discretization. Let's divide the structure into members and nodes and determine the degrees of freedom. We will not need it to draw the internal force diagrams, but to repeat what we have learned, I will do it. Now, first, the discretization starts with assigning nodes. At point A, At point A, we have a discontinuity, right? We have a support, so I should have a nodal point here. At point B, the geometry changes. We have two members here. At point C, I should have a node, and at point D, I should have a node. So let's draw the nodes first. Point B, point C, let's show it this way. At point A, I have a support, a pin support at A, and I have a roller support at D. So by definition, between two nodes, we have a member. So I have member BC, I have member AB, and I have member CD. So when I look at this structure, so I no longer see a continuous structure, but I see a structure that's composed of 4 nodes and 3 members. Now, the next step is to go node by node and assign degrees of freedoms. Now here, I will not make any simplification, so I'll just say no axial rigidity. And let's go node by node. So the first question, I'm at node A right now. The first question, can it translate in the horizontal direction? The answer is no, so I don't assign any degrees of freedom. Can it translate in the vertical direction? The answer is no, no degrees of freedom. Can it rotate? The answer is yes, so I'll assign my first degrees of freedom to this point. Jump to the second node. So we are asking these simple questions. Can it translate in the horizontal direction? The answer is yes. That's my second degrees of freedom. Can it translate in the vertical direction? The answer is yes. That's my third degrees of freedom. Can it rotate? The answer is yes. That's my fourth degrees of freedom. So I'll continue this way. Now I'm at node C. Can it translate in the horizontal? Yes. D5. Can it translate in the vertical? Yes. D6. Can it rotate? Yes. D7. Finally, node D. Can it translate in the horizontal? Yes, it's a roller support. D8. Can it rotate? Yes. D9, and it cannot move in the upward direction. So this structure has 9 degrees of freedom. Now, when we look at this structure in terms of forces, we have 2 unknown support reaction here, 1 unknown support reaction here. So total unknown support reactions are 3, and I can write 3 equilibrium equations. So this is statically determinate case. But when it comes to the kinematic indeterminacy, as you see, the degree of kinematic indeterminacy is 9. So let's see what will happen if we assume axial rigidity. So I'll just draw the same figure one more time. Roller support here. That's a node. That's a node. Of course, again, we have 4 nodes. We have 4 nodes, 3 members, and now I'm assuming axial rigidity. Remember that the axial rigidity assumption assumes that the axial deformations of members are negligible. We can ignore them. Why are we using it? To simplify the solution. And most of the civil engineering structures we can assume, especially if it's reinforced concrete, we can ignore the axial deformations. So again, let's determine the degrees of freedom. So at point A, again, we have D1. So let's go to point B. Can it move in the horizontal direction? The answer is yes, because I don't have any support. So let's put the degrees of freedom here. D2. Now, can point B move in the upward direction? The answer is no. Why? Because I have a support at this end of this column. And if this point move in the upward direction, then this column should elongate. And which is not possible because it's axially rigid, no deformation. So there is no vertical translation. So we don't have any vertical translation. That translation equal to 0. The third question, can it rotate? The answer is yes. So we have the third degrees of freedom here. Let's jump to node C. Can it translate in the horizontal direction? The answer is yes, but there's a constraint. If this point moves in that direction, I should have the same amount of translation at point B. In other words, point B and point C should move by the same amount towards right or left in the horizontal direction. So in order to make sure that these 2 points move in the same amount, I'll just say that that's also equal to dt. We have a d2. We have a degrees of freedom, but the magnitude of that degrees of freedom and this one should be the same. This way, I don't see any shortening and elongation at this member. Can it move in the upward direction? Again, the answer is no, because it will cause elongation in this column. So I don't have a degrees of freedom there. Can it rotate? The answer is yes. Then we have the fourth degrees of freedom. Now let's jump to node D. It can translate. So this is the fifth degrees of freedom, and it can rotate. This is the sixth degrees of freedom. So when we assume axial rigidity, we end up with 6 degrees of freedoms. And as you see, now with this assumption, the degree of kinematic indeterminacy decreases to 6. Of course, we will see how to analyze such structures later on, but just as an exercise, we see how we do the discretization and assign degrees of freedoms. So let's erase this and come back to our problem. Let's take a look at the unknowns. I want to calculate the support reactions first. This is AY, this is AX, and dy. Okay. Then I should write the equilibrium equations. So the first equilibrium equation is sum of forces in X must be equal to 0. So this gives me that 10 plus AX must be equal to 0. So AX is equal to minus 10 kilonewtons. The second equilibrium equation, I'm taking moment with respect to point A. So the sum of moments at point A must be equal to 0. So that's the positive direction. So I'm taking moment with respect to point A. So dy will create a moment in this direction, and it's the same direction with my positive direction. So 5 times dy. We have this distributed load. This distributed load will create a moment in this direction with respect to point A, and that's the opposite direction of my positive direction. So we got minus 5 times 5 is the magnitude of that distributed load, times 5 over 2 is the moment arm. And we also have this point load here, and it will create again a negative moment. So I got minus 4 times 10, 4 being the moment arm. And from that equation, I obtain dy as equal to 20.5 kilonewtons. And my final equilibrium equation, Fy is equal to, should be equal to 0. And this will tell me Ay plus dy minus 5 times 5 should be equal to 0. And from that equation, I obtain Ay as equal to 4.5 kilonewtons. So these are the support reactions. This is equal to 4.5. This one is equal to 20.5 kilonewtons. And Ax, let's me correct the direction now. We know the direction at this point, so it's in this direction, and it's equal to 10 kilonewtons. So we calculate all the support reactions. Now I have to draw the free body diagram. So from now on, the way we will be drawing the free body diagram is as follows. We will be working on the discrete version of the structure. So we are drawing the structure as composed of members and nodes, like that. Now here I'm showing a loading on this member. So for now, this is the member load for me according to my discretization. And I got 10 kilonewtons here. And this 10 kilonewton is a nodal load for me. Okay, now let's show the support reactions also. So here at this node I got 4.5 kilonewtons, and in this direction I got 10 kilonewtons, and at point D I got 20.5 kilonewtons. So this is everything I know about this structure right now. Now this is a point. So this point should be in equilibrium. So in order for this point to be in equilibrium, I should have the same forces but in the opposite directions. Okay, after showing it this way, now this node is in equilibrium. All the forces are in equilibrium. I don't have any moments because this is a point. Now I have a section cut here, right? I cut it this section and divide this member into two. So I should have the same forces, but they should be in the opposite directions. So I'm done with this node. Now let's take a look at this member now. This member should be in equilibrium. So, yes, yeah, let's use it this way. So the force here, the sum of forces in X must be equal to 0. So this should be equal to 10 kilonewtons. The sum of forces in Y must be equal to 0. So I should have 4.5 kilonewtons here. And if I take moment with respect to that point, this 10 kilonewton will create a moment in this direction. So I should have another moment here in that direction to balance the moment due to that 10 kilonewtons. So this will be 10 times 4, 40 kilonewton meter should be the end moment at point B. Now, if you take a look at this member is also in equilibrium. Now from the member, let's jump to the node. I have a section cut here, so I got 10 kilonewtons, 4.5 here, and the moment as 40. In order for this node to be in equilibrium, I shall have the same forces in the opposite direction. These two forces, 10 kilonewton and 10 kilonewton, cancel each other. So at this end, I only have a vertical force and the moment. Transfer this moment to this member. So at this end of the member, I have a moment that's equal to 40 kilonewton meters and a shear force that's equal to 4.5 kilonewtons. So after that step, this node also is in equilibrium and we transfer the end forces to that member. So let's switch to the other side. For equilibrium, I should have 20.5 kilonewtons here. 20.5. And at this end, I should have another reaction that's equal to 20.5 kilonewtons. And these are all 20.5 kilonewtons. Now, we are done. All the nodes are in equilibrium, as well as all the members are now in equilibrium. So with the free body diagram, we show all the forces at the nodes and the members. After doing that, now we are ready to draw the internal force diagrams. So let's do that. But before drawing them, we should define our sign convention. So here I am showing the positive direction. For the axial forces, the tension is positive. These are the shear directions, and these are the positive moment directions. So let's start with the axial force diagram. Let's sketch the members. So this is the axial force diagram. So I'm showing these members like that. Columns are bottom to top, beams are left to right. Okay. Now let's take a look at this sign convention. It says that if the member is subjected to tension, it's a positive force for me. Now, while drawing the internal force diagram, we go member by member. Okay. So I'll start from the first member. It's under compression and the compressive force is 4.5 kilonewtons. So let's draw it. Let me use a different color. This is minus. It means that this is compression. That's 4.5 kilonewtons. The second member is this one. I don't have any axial force, so 0 here. And this is the third member. Again, it's under compression and the magnitude of compressive force is 20.5. So let's show it this way. minus 20.5 kilonewtons. And that's it. We drew the axial force diagrams. Of course, while drawing the axial force diagrams, we didn't use this arrow because it's easy to figure out the sign of the force. If its tension is positive, if it's compression, it's negative. Now let's take a look at the shear diagram now. We will be using these arrows while drawing the shear diagram. Okay, so these are the arrows. Again, I'll go member by member. This is the sign convention. It shows the positive direction. Now I'm looking at this member right now, and the way we define it, it's going from bottom to top. So I should rotate that sign convention like that, so that this arrow will go from bottom to top. And when I rotate that arrow by 90 degrees, at the bottom, the direction of the positive shear is as follows. It will be this way. I'm comparing it with this one. They are in the same direction. So I have positive 10 kilonewtons at the bottom. This is 10 kilonewtons. So I'll do the same thing. Rotate that by 90 degrees. So this will be the sign convention. At the top, let me draw it one more time. At the top, the positive direction is as follows. That's the positive direction. Compare it with this one. They are in the same direction. So at the top, I also have plus 10. What about the variation in between? I'm looking at this member. I don't have any loading. So variation should be linear. And I'm just connecting these 2 points, start and end points. Okay. So let's jump to the second member now. This is the sign convention. This is the forces on the second member. On the left hand side, both directions match. So left hand side, I should have a positive shear. This is 4.5 kilonewtons. At the right hand side, the positive direction is in the downward direction. Here, the shear force is in the upward direction. This shows that at this end, I have a negative shear. So here we have a negative shear. Magnitude is 20.5 kilonewtons. What about the variation? Now, the force is uniformly distributed load, and the variation is 1 degree above that, which is a linear variation. So this is plus, this is minus. While drawing that, I said linear variation, but it's wrong actually. I don't have any loading on this one. So the shear should be constant. And as you see, we have a constant shear. Let's go to the third member. I don't have any shear force on the third member. So this is equal to 0. And our final internal force diagram is the moment diagram. So our approach is the same. With these arrows, I can show the directions. Now start from this first member again. I'm rotating that by 90 degrees, and this time the direction of the positive moment is as follows. And I'm comparing with this 40 kilonewtons. They are in the same direction. So at the top, I have a positive moment. A positive moment magnitude is 40 kilonewton meters. At the bottom, it's 0. What about the variation? So I'm looking at the shear diagram for that. I have a constant shear, which tells me that I should have a linear variation in the moment. And this is plus. So let's take a look at the second member now. At the start node, this is the direction of the positive moment, and it's the same with this moment here. So again, I should have plus 40 here. At the far end, the moment is equal to 0. I should have a 0 moment here. What about the variation in between? So a uniform distributed load gives me linear variation in the shear. So the variation in the moment should be quadratic. But the question is, will it vary like that or this way? Which one? So in order to figure that out, I have to take a look at the shear diagram. So the shear diagram tells me that the moment should increase first, and then we have a negative area, which means that after that point it should decrease. So it should increase and then it should decrease, and this is plus. How much force do I need? What's the maximum moment? It's the 40 plus this area. Okay, and when you do the calculations, you'll find out that this distance is 0.9 and the maximum moment becomes equal to 42.025 kilonewton meters. So as you see, when we do the discretization like that and show all the forces at the member ends, drawing the internal force diagrams are nothing but drawing the internal force diagram for a simply supported beam. Let's consider this member, for example. Once we have that free body diagram, you can just consider these two forces as your support reactions with an end moment that's equal to 40 kilonewton meters. So drawing the internal force diagrams is exactly the same as drawing the internal force diagram for a simply supported beam. These arrows will help me to determine the direction of the forces at the beginning and ends of the members. So here I define my members going from bottom to top. So I rotate that sign convention by 90 degrees. When you do that, this will be your sign convention, and these are the positive directions of the shear. So with the arrow, we will determine the positive direction for members that are not horizontal. Okay, again, drawing the free body diagram, drawing the internal force diagram of this member is very similar to drawing the internal force diagram for simply supported beams. And also you should always remember, here I have a uniform distributed load, which tells me that the shear diagram should be linear. We have a linear diagram, and the moment diagram should be a parabola, a quadratic parabola. Here I don't have any loading, just end shear forces, so I should have some constant shear, which gives me a linear variation in the moment diagram. So as I said before, from now on, we will always be drawing the free body diagram. It doesn't matter how simplified, how simple your structure is, we will divide it into nodes and members and show the free body diagram and all the forces at the nodes and at the members. Our second frame example is very similar to our previous case, but we add a minor difference to it. So we have the same geometry, but we'll have a fixed support here, and we define an internal hinge at point B. We have the same beam, same column, and the roller support here. Let me draw the length of this column. It's 2 meters. We have again uniformly distributed load here. Magnitude is 5 kilonewton per meter. I have a point load at 10 kilonewton. This one is an internal hinge. We will discuss its behavior. The height of the column is 4 meters and the length of the beam is 5 meters. Okay, and this is point A, B, C, and D. So again, we will try to draw the internal force diagrams, but before going into that, again, I will do the discretization. So let's determine the nodes now at point A, node, point B, point C, and point D. We have 4 nodes. Let's draw them. I have a hinge here, point B, point C, member AB, point A, member BC, and member CD, and point D. And let's show that we have nodes here. Okay, now basically again we have 4 nodes and 3 members, and I will determine degrees of freedom with axial rigidity. Okay, but before going into the degrees of freedom determination, let's repeat the behavior of an internal hinge. Remember that we discussed internal hinge as follows. Assume that I have 2 members here, the first member and the second member, and we say that this member is free to rotate at this point. It can rotate in any direction, and this one also free to rotate. In other words, if the member on the right rotates, it has no effect on the member on the left. It can stay this way. So this actually creates a rotational independence between these 2 members, this internal hinge. But let's draw another deformed shape. If this point moves by delta amount, both members move the same amount. But this member has a different rotation than this member. Okay, this end is free to rotate. How does this member behaves if, let's say that I don't have any internal hinge, and let's say that this point move in the downward direction by delta amount, then we would have the same rotation at both ends of this point. So the same rotation will occur on the left hand side and the right hand side. We have a single rotation. But when I put an internal hinge here, I can have 2 different rotations at both sides of the hinge. It's the same here. Now in that case I have an internal hinge like that. So let's say that if this member rotates by that amount, let's say this is theta 1, this member can rotate in a different rotation, or it may not rotate at all. So in order to show that, we can just say that I can have a rotation as follows. Theta 2 and theta 1 doesn't have to be equal to theta 2. Okay, so let's keep that in mind, and now start drawing the degrees of freedoms. So at point A, it's a fixed support. I don't have any degrees of freedom. Now let's go to point B. Can it translate in the horizontal direction? The answer is yes. That's D1. Can it translate in the vertical direction? This point cannot move. If it moves in the upward direction, I will see an elongation in this member. So the answer is no. I don't have any vertical translation at B. What about the rotation? This is the exaggerated version of that member, and as you see, I can have 2 different rotations. So in order to show that, I'll just say that the rotation at this end of the member is D2, and the rotation at the other end between point B and C is D3. So this way I define 2 different rotations like this case. So here I got 2 different rotations and 3 degrees of freedoms. Point C, as we discussed before, it will move in the horizontal direction but with the same amount of point B, so that this member will not elongate. It cannot move in the upward direction because this cannot elongate, but it can rotate, and since this is a rigid joint, a continuous joint, I will have a single rotation, and that rotation is D4, and node D, this is D5, and that's D6. So basically in this structure we have 6 degrees of freedom. If you want, you can repeat it for the no axial deformation case. Okay, now let's determine the support reactions, and from the support reactions let's calculate the free body diagram and the internal force diagrams. So here let's show the support reactions. I got AY, AX. Now this is a fixed support, so I should have a moment. Sorry for this bad drawing. Yes, that's MA, and I should have another support reaction dy here. So let me erase this portion and write down the equilibrium equations and try to determine these support reactions. So our first equilibrium equation is sum of forces in the x direction is equal to 0. So this gives me 10 plus ax equal to 0. So here we find out that ax is equal to minus 10 kilonewtons. So what I'm going to do is I'll divide this structure into two from this point. So on the left hand side, this is the structure that I see. Five kilonewton per meter. I got dy here. And on the right hand side, I got 10 kilonewton point load here. That's the fixed support. So we already calculated our AX, which is equal to 10 kilonewtons. I got AY here and a moment that's equal to MA. Okay, so let's start from this free body diagram. I know that at this point moment is equal to 0. That's point B. So moment at B is equal to 0. So this tells me that 5 times dy, I'm taking moment with respect to point B, minus 5 times 5 times 5 over 2 should be equal to 0. And from that equation I obtain dy as equal to 12.5 kilonewtons. And then I'm looking at this free body diagram right now, and I know that moment at B is equal to 0 and B is equal to 0. So from that equation, 10 times 4 plus MA should be equal to 0. So what I did here is I'm taking moment with respect to that point. I have a moment due to 10 in this direction plus MA should be equal to 0. So this, from that equation I obtain MA as equal to minus 40 kilonewton meters. And then my final equilibrium equation will be sum of forces in Y is equal to 0. So AY plus 12.5 should be equal to 25, which is the total vertical force due to this uniformly distributed load, and I obtain AY as equal to 12.5 kilonewtons. So with this equilibrium equations, I calculated all the support reactions. Now let's calculate let's determine the free body diagram. So I will draw the free body diagram in here. Free body diagram, and remember that we are drawing the free body diagram by looking at the discrete version of the structure, node B, member BC, node C, member AB, node A, node C, member CD, and node D. I have a point load that's equal to 10 kilonewtons in here, and a uniformly distributed load that's equal to 5 kilonewton per meter. Okay. So let's show the support reactions. So I got 12.5 kilonewtons here. AX is in this direction. That's 10 kilonewtons. And the moment is in this direction. And magnitude is 40 kilonewton meters. And at D, I have a vertical support reaction that's also equal to 12.5 kilonewtons. So I'm writing the equilibrium equation. I'm starting from this node, writing the equilibrium equation for that node. So I have 10, 12.5, and 40. Now node A is in equilibrium. So I should transfer the forces, 12.5 kilonewtons, 10 kilonewtons, and that's the 40 kilonewton meter moment. Now I'm writing the equilibrium equations for this member. In that case, I have 12.5 kilonewtons, 10 kilonewtons, and we know that moment is equal to 0. Transfer them to node B. I got 10 kilonewton and 12.5 here. These two 10 kilonewtons, they cancel each other. I got 12.5, and here 12.5 kilonewtons. Then I'll go to node D, 12.5 kilonewtons, 12.5, and here I got 12.5 kilonewtons. So I show all the forces. Now all the members and all the nodes are in equilibrium. Now we are ready to draw the internal force diagrams, and let's do that. So in order to do that, we will just first show the sign convention plus these are our positive directions. This is the positive direction for shear, and these are the positive direction for moment, and this is my sign convention. So let's draw the axial force diagram first. This is our structure. So let's start from member AB. It's under compression. Magnitude of the force is 12.5. So since it's under compression, it's a negative axial force minus 12.5 kilonewtons. Member BC, no axial force on it. That's 0. And member CD, I got compressive force magnitude is 12.5 minus 12.5 kilonewtons. That's the axial force diagram. Now let's draw the shear force. Let's draw the structure one more time. So my structure is going from bottom to top. So I have to rotate that sign convention as follows, bottom to top. And in that case, that's the direction of the positive forces. So at the top I got the same direction of the force. At the bottom they are in the same direction. So here I have a constant shear force, a positive constant shear force, and whose magnitude is 10. So constant shear force, the magnitude is 10 kilonewtons. Let's take a look at the second member. On the left hand side they are in the same direction, so I have positive 12.5. On the right hand side they are in the opposite direction. I should have negative 12.5. And the variation, I have a uniformly distributed load here. Uniformly distributed load here. Oops, sorry for that. I go to a different. Yep. Yeah, a uniformly distributed load. Variation should be linear. 12.5 kilonewtons. 12.5 kilonewtons. This is plus. This is minus. And no shear force on member CD. That's 0. That's the shear force diagram. And finally, we should have the moment diagram. Again, I will be using this sign convention. Rotate that. So at the bottom, that should be the direction of the moment. And if you take a look at this one, they're in the opposite directions. So I'll start with a negative moment. So it's minus 40 kilonewton meters. At the top, the moment is equal to 0. We have an internal hinge. The variation, take a look at this one. The variation, shear is constant, so the variation is linear. And the area underneath is positive, so the magnitude of the moment should change in the positive direction. So that should be the variation, a linear variation plus. So member BC, at both ends the moment is equal to 0. So 0 here also. What about the variation? I can look at the shear diagram again. So I will have first positive moment, 0 slope here, and moment starts to decrease afterwards. So that's the shape of the moment diagram. And you can calculate the magnitude of the maximum moment by calculating the area of this shear force. So as you see, once you draw the free body diagrams of every member, drawing the internal force diagram is a very straightforward process. You go member by member, look at the forces, compare it with the directions of the sign conventions, determine the locations of the end forces, and then take a look at the loading or take a look at the shear diagram to determine the variation between these 2 points. Now for member AB, for example, I don't have any loading, so the shear force should be constant. If I have a constant shear force, I should have a linear variation in the moment. Let's take a look at member BC. At member BC, I have a uniformly distributed load, which tells me that the variation of the shear should be linear, and also the variation of the moment should be a quadratic polynomial. So once you draw the free body diagram as we described here, drawing the internal force diagrams or the equations for these internal force diagrams are a very straightforward and simple process.